astroparticle physics, and it should be in the definition of the European, which includes gravitational waves and all kinds of extra things. So the Americans invented particle astrophysics, the Europeans moved the astro around and included more stuff so that the same particle physicists can do all kinds of interesting astrophysics without being penalized. It's a marketing technique that started in Chicago. All right.
Okay, so thanks everyone for being here. The plan is to have 3 short talks and then we'll have a discussion. And the first talk is by Katie Fries, who got her PhD here at AstroChicago. She's a professor at Michigan and she's also director of NORDITA.
So is the microphone working?
I can't tell if the microphone's working?
Yes, it is.
Okay. Is there a pointer?
There it is.
Okay, so we've now figured out where this is. It's right over there. So that's me and Dave Schramm. And I don't usually mix up tennis and baseball, but anyway. So this was these were the days of the creation of particle astrophysics. And without this wonderful giant of a man, physically and mentally, I'm not sure how many of us would be here now. So well, I guess I certainly wouldn't be. And so you know he was Olympic hopeful in wrestling, and you should have seen him skiing moguls. They would just get out of the way. And
Unfortunately, not for us behind.
yeah, you have to work pretty hard to try to keep up.
They close after.
Yeah, they close after he's gone. Yeah, we get double blacks, right? Non-stop. But then uphill was a little harder for him.
That's
You know, weight matters. Way up. And he was one big guy. And wonderful and one of the creators of this field. So eternally grateful to him. And so my other mentor, Mike Turner, and I love this picture. This is when he came, this is, I don't know, 10 years ago, University of Michigan. He gave a public lecture. There he is. So, I didn't really know what to do with this little mini talk, so I thought I'd start by asking what are the big questions now. And I guess before I even do that, let me put myself back in the frame of graduate school. Nobody would have thought we were going to get the geometry of the universe in 25 years, or whatever it was. Less than that. Nobody would have thought that, oh, I remember a very big name in the field, a very good friend of mine, saying, nothing about inflation will ever be tested. Why are we writing down all these different models? Okay, so the amount of data that have come in have been not only staggering, but unexpected. So the idea that we're supposed to predict what's going to happen in the next 25 years, honestly, to my mind, is absurd. So what you can do is build stuff and go look, which is what you told us about yesterday, and that is the way to go. And one thing that hasn't been talked about much, but if you're going to be an astroparticle, is LHC. They're doing exactly that. So if you ask what did they have in mind when they built it, number 1, the Higgs, they got it. Number 2, SUSY and or dark matter, a little more problematic, nothing but balanced so far. On the other hand, now that they've doubled their energy, they have access to particles, SUSY particles that have only electroweak interactions, whereas before it had to be through strong interactions, so they have access to a whole new regime, so maybe. And I don't have the chutzpah to guess whether they're going to find anything or not. And the third thing they want, of course, is the unknown, and here the data become an issue because they're throwing most of it away. Not even putting it on in tape, it's just going into the air. Basically, so the theory just helps them decide what to say. That's kind of scary. But, so let's hope between astronomy and particle physics we get something really radically new, exciting, da-da-da-da-da. But as far, I did want to say, okay, so from my point of view, big questions in astroparticle right now would be these: inflation, dark matter, dark energy, and my most recent baby, dark stars. So, okay, so where are we now? Well, my famous friend who said it could not be done has been one of the people who's done it. And inflation made generic predictions, and they're all right. This is really kind of weird and amazing. Okay, so I'm not going to talk about them all. Flat universe, density perturbations near 1, a special index, super horizon correlations, adiabatic. Okay, this one we're still waiting for. So you have the generic predictions, and now we're testing in between models. Wow. And One thing that's really key, very powerful bounds on non-Gaussian entities from Planck means most models are dead. The only thing left are the really simple models. One field rolling down one hill, the simplest vacuum, the simplest kinetic energy, simple, simple, simple. That didn't have to be. I mean, the world's complicated, so I'm very happy about that. Because, okay, the three of us had a good idea in 1990. We wrote down what it would take to kill the model, but here we are, still talking about it. Use axioms for natural inflation, so that could either be the cosine, this purple thing, or axiom monodromy, which, yes, is also an axiom. That's why it's called axiom monodromy. So our brilliant idea of using axioms has a new offshoot that everybody loves. But I had to say that, Angela. No, she's happy. I know she wanted me to do that. So anyway, okay. So sadly, we now are at this purple line here. Different repeating models, okay, but we're in tension at 2 sigma. So we quickly move on to the next slide. Mine is okay because the other axiom, the cosine is on the area edge. Well, it's at 2 sigma. The other guys are still alive. Okay, so my predictions. Okay, B modes will be found. Natural inflation is right, of course. So either R is 0.3, which is what we need for the cosine. Oh, 0.03 for God's sake. I've done this so many times. So either that's right, or you get a linear potential is kind of monodromy ideas. But no, but seriously, I'm of course really optimistic that we find these guys. Something people want to talk about, there are alternatives to rolling models, and those are tunneling models. So this was Allen's original model, which failed, the original version failed, but there are other ones where you can finish end inflation with tunneling. Well, in that case, there are bubble collisions, and depending on the scales, you can find that in advanced LIGO. So my student Alejandro Lopez has worked that out. So it's another thing that could happen. Okay, so in 25 years, multiverse is dead, no longer needed, because smart people came along and had physical mechanisms instead of throwing it into the insoluble. I also have talked to me about eternal inflation, which I don't think is a problem. The accessible part of inflation, delta rho over rho equals, let me back up. To have eternal inflation, that's the part of the potential where delta rho over rho equals 1. That is nowhere near anything we're testing. That is not inside our horizon. It's way, way out there somewhere. And I'm not worried about it. Okay, so it's Transplanckian or whatever, I'm not worried about it. But anyway, so no one will be talking about this anymore in 2042. And spectral distortions can actually teach us about inflationary potentials outside of the realm that is currently observable, so that will be cool. Okay, pie chart of the universe, these are the big boys, we've got to get these. So dark matter we know something about and we're going to get. Okay, so many candidates. Today there are anomalies in the data. The question is, will any of those hold up? Okay, LHC so far nothing, but that doesn't mean much yet because the bounds they show are always for very restricted models where there are only 5 parameters. Well, there are actually 105 of the minimal supersymmetric standard models, so these pictures don't necessarily mean that much. Okay, gamma, weird, hanging in there, and modulation, which I have a personal affinity for reasons that so still hanging in there. What the hell is that? Will be tested at both in the southern hemisphere, SAPER's Princeton, Australia experiment, and in the ice. So that's now I'm looking short term. That's it's gonna survive or not soon. Okay, so we have Hoopers, this gamma ray excess at the galactic center. So that's anomalous signals, another anomalous signal, the 3.5 keV line, which could be sterile neutrinos. There's also an integral signal, which could be MEV dark matter, a lot of anomalies. And I'm not going to speculate as to whether or not any of these will hold up, but I will predict that we will know in 2042 because we will be sick of looking for WIMPs, for axions. By the way, it doesn't have to be a QCD axiom. There's other quote-unquote axioms, ALPS, that are also going to be tested. Light dark matter, sterile neutrinos, something new. I don't know. I think we're going to get that. And then we're going to use directional detection to map the dark matter distribution in the Milky Way. That will be very cool. You can learn about streams, you can learn a lot once you get the dark matter and such. This is one of these things we worked on. You have gold with DNA hanging from it. You can track what direction the wind came from. So we're going to build that. Okay, so if that was inflation, dark matter, if dark matter is made of WIMPs, then dark stars exist, and James Webb will find them. These are the first stars to form in the history of the universe, can be powered by the same dark matter annihilation that gives you the galactic center excess. I want to point out, these are stars made of hydrogen, mostly little, very tiny amount of dark matter. But dark matter is a very powerful source, and these things stick out in James Webb. There'll be H-band dropouts or whatever. They will be discovered, of course. A new type of star, no fusion, dark matter, the power of darkness, and you have to have pulsations to tell the difference between them and other things. Okay, dark energy. Honestly, I give up. So observation is very difficult. Theory impossible. I tried something with that Cardassian cosmology, but there's a lot of really smart ideas out there. I really like massive gravity lately. I think that's pretty cool. The epicycles. Dark matter exists. Dark energy, I'm not even sure exists. So I could tell a joke about it, but since Mike Turner's not here, it's not as fun. Okay, so this is the three of us talking about dark matter at a World Science Festival in 2011. There's these three were talking about dark energy, and there's Mike. I had a true statement about it. That's about all I know about dark energy. Okay, so, all right, so I think inflation is right. We'll find the gravity waves. I think we'll find the dark matter. If it's WIMPs, we'll find dark stars. And actually, I take it back. I don't know what we'll know about dark energy. We want new physics. The boldly go where no one has gone before, and there's Captain Janeway. Okay, that's it.
So we're not going to take any questions at this point. We're going to hold that to the second half when we have our panel structure dialogue. We're going to hear another short presentation on the more cosmic ray direction.
So next is Nico Gutera, and she was a postdoc at UChicago, and she's now faculty at the IAP.
And I'm also visiting here for 3 months, and it's really great to be back here. So I'm going to talk more about the particle side of astroparticle physics, and not leave gravitational waves also to create. So, while thinking about astroparticle physics, we have to remember first that almost all of these astroparticles are connected to cosmic rays. So, you know what cosmic rays are, so charged particles that constantly bombard the Earth. This is the flux that we get of cosmic rays on the Earth. So it's really nice, nearly power law flux that extends over more than 10 orders of magnitude in energies and more than 30 orders of magnitude in flux. So at lower energies, we know that cosmic rays come mostly from the sun, but as we go to higher and higher energies, we're less sure about where they come from. So around, say, below PeV energies, we believe that we have good hints that cosmic rays are accelerated in supernova remnants. There could be subcomponents like electrons, positrons, and protons that are accelerated in other objects like pulsars, or that are from dark matter. But then, as we move to the highest energies here, so you might have noticed, that we receive cosmic rays at above 10 to the 20 electron volts, which is many orders of magnitudes above what the LHC can currently probe. And at these energies, we still don't know what the sources of these cosmic rays could be. So this is, I think, one of the biggest puzzles in astrophysics that we have currently, and what we've endeavored to solve for I would say, more than 30 years now, 60 years, 100 years, maybe. So yeah, this is hopefully by 2042 we will have actually have an answer to that question. Well, it's not just everything, all astroparticles that are connected to cosmic rays. The University of Chicago has always been working on this field, starting with the ICRC starting probably with Compton, Fermi, the ICRC in 1939. Lots of people who worked on that, of course, Jim Cronin, and many faculties today working on this subject. So why do I say that everything is connected to cosmic rays? Well, so I said that the puzzle is that we have something out there accelerating cosmic rays. We don't know what it is. And these cosmic rays are going to, while they travel in space, they're going to interact with radiation or hadronic matter and produce neutrinos and gamma rays. And these particles are also going to travel to us. And what happens is that they cross the intergalactic medium. Neutrinos come straight to us. Gamma rays come nearly straight to us, but they might encounter a photon in space and thus be limited in their propagation. And then there are cosmic rays, which are very much influenced by the magnetic field that swamps our whole universe. And cosmic rays are going to be deflected, and thus we are going to lose their origin. That's why it is such a difficult question. The source for the origin of cosmic rays is such a difficult question to answer. So, well, this is why it's very difficult to, so neutrinos, it's very hard to observe because they're not very interactive. Cosmic rays are bent, and gamma rays have a horizon. This is why it's so difficult to play with each of these messengers, and we want to do multi-messenger astronomy. Combine all these particles together, plus gravitational waves, to try to solve the question of the origin of cosmic rays. So this is what these people are working on, and they're using many facilities that are available that have been built that are in operation today. So there is the Auger Observatory, Telescope Array, Veritas, Magic, HESS, Fermi in gamma rays, spanning from GeV energies to TeV energies, to hundreds of TeV energies. And in neutrino we have Anita and IceCube. So combining all this, today we are still, we don't have an answer yet, right? So what happens in 30 years? So, well, I have no memory to share about 30 years ago in astrophysics personally. So then I went to Google and I looked for books. And one book I found was Astronomy and Astrophysics in the 1980s, so 30 years ago. And so what it was written by the Astronomy Study Committee, and the representative of the University of Chicago was Eugene Parker, who's very involved in cosmic rays, of course. So I looked and I didn't read the whole book, but I looked at the chapter that was of interest for us here. And what I saw was violent events, cosmic rays, supernova impulsors, and basically there was, there was only textbook knowledge on supernovae. So this was kind of surprising, well, to me. And also nearly no mention of gamma rays. Maybe the word was there like twice in the book. So I think, and I hope most of you agree, that probably the major breakthroughs that happened in the last 30 years in this field are gamma ray astronomy and the explosion of supernova 1987A. So, well, because gamma ray has completely opened a new window, we have a whole bunch of telescopes that have been built since and that are collecting lots of data. And of course, supernova 1987A has brought lots of data and answered many questions about bad events. So if we translate this to 30 years from now, my guess then is that the major breakthroughs are going to be neutrino astronomy and another local supernova, 2030 something, or maybe 2020 something. So,
Maybe 2042.
yeah, but that's actually too far. I would rather have it before. So not too fast because we need our facilities to be built. But yeah, so it's an easy guess. But so that's my easy prediction. And so as for neutrino astronomy, so to be a bit more precise, I would say that by 2042 we would have detected thousands of neutrinos, not counting those coming from this one. And hopefully we will have a dozen of neutrino sources identified. I think with thousands of them, it's quite easy to do so. Well, easy. So, and also that we will have seen time variable signatures of neutrinos, meaning transient sources observed in neutrinos. So I think this is pretty feasible because so this is the cosmogenic neutrino flux, some predictions. So you know cosmogenic neutrinos are those produced by ultra-energy cosmic rays that propagate in the intergalactic medium and encounter significant photons. And they produce neutrinos for which the flux can be calculated, knowing that we observe a certain amount of ultra-energy cosmic rays. So the standard prediction lies in this gray region here, and the most pessimistic predictions are down here. And so the current projects go down here and even down here. So we are actually trying to already envisage a detector that could be built in the 20s that would guarantee the detection for the most pessimistic models. And if nature is nice with us, we will see more than hundreds of events in these usual standard models. So, and this is, the red line here is a line as the sensitivity of ground, which stands for giant radio array for neutrino detection. The deployment is envisioned for the 2020s, and it's a huge scalable project, meaning that we could build one ground and build many others, and this would just multiply, enhance the sensitivity, and then we could reach thousands of neutrinos that we would want by 2042. So I think that's pretty likely. Actually, it's quite restrictive to talk just about neutrino astronomy, because if neutrino astronomy happens, it also means that we can do multi-messenger astronomy, and this is much bigger. So multi-messenger astronomy means combining gravitational waves, that I'm not going to talk about, but also cosmic ray data and gamma ray data, and putting them together in a network. So with CTA, for example, we are already, and this is much sooner than 42, it's like in 10 years or so. So my prediction for 42 is that we will have, with CTA and maybe a successor or some bigger scale project, an enhancement or something, a catalog of more than 700 TV sources in 9 different source classes, and among which Angela was predicting that there would be more than hundreds of them unidentified sources which have no counterparts in other wavelengths. So this would be nice, but also in cosmic rays we could have something like GEMUSO built. GEMUSO is a project with space satellites that would measure the air showers of ultra-energy cosmic rays from above, and it plans to detect thousands of ultra-energy cosmic rays, and then we should identify for sure a dozen of sources, even if the composition of cosmic rays is heavy. This is studies show this. So if this satellite flies, we're pretty sure that some sources of ultra-energy cosmic rays will be identified for sure. So this is another nice progress. So we have neutrinos, cosmic rays, gamma rays, and then we need to build something that connects everything together. So there is currently a project at Penn State, so I'm sorry I'm talking about another university, but that's what they're doing. So it's called AMON, so Astrophysics, Astrophysical Multi-Messenger Observatory Network. So I think that this is still small scale to some extent, but we should go bigger, and then we will be able by 2042 to send alerts to all multi-messenger and all wavelengths observatories. Whenever an event is observed, for example, neutrinos, we go through it, everybody points to this direction, and then maybe we can identify transit sources. So that's for multi-messenger astronomy. And then, so if we have all this ready, so it should not happen too fast, this supernova. But then, if everything is ready to, all this is built, we will be ready to scrutinize the explosion of the next local supernova. So you know that the rate is like 1 every 60 years. So we should think we're good. It should happen by 2042. I mean, it would be very unlucky otherwise. So, and then that would be really cool because we could do probe particle exploration regions, the energy, the energy budget of the supernova, all the mechanisms at play. With something like CTA and maybe better, we could observe 10 parsec scale gamma ray features, which is just crazy. We would be able to do precision neutrinos, to trace precision neutrino spectra from this supernova. Probably even see like some timing, well, maybe not with hundreds of events, but maybe some timing, time variabilities. Yeah, but of course, actually, we would not see the cosmic rays coming from that direction because, well, unless it's very close, we will, because of the deflections in the galactic magnetic field, we would have to wait for more 30 to 60 other years before the actual cosmic rays come to us. So, well, that's still great.
This is a prediction for 20.
Yeah, 760. Yeah. And yeah, so other more detailed stuff that I could predict are, for example, with SKA. So I think that by 2042 we will have a very nice map of the intergalactic magnetic field, at least above 1 nanogauss. In that case, we will be able to do actual propagation of cosmic rays in the universe and even go back to the source and do a precise study of the deflection, which is just impossible currently because we have zero idea of what the magnetic field outside our galaxy is, outside of clusters of galaxies. So this would be another big thing. And also theorists and people who do big simulations will probably have made a lot of progress as well because of computing power, and they will be able to so particle in cell. Sorry, particle in cell. Yeah. So that's a type of simulation where you do plasma, evolved plasma image. Yeah. And you can calculate, for example, the acceleration of particles with feedback of on the plasma. And it consumes a lot of computing power. So right now it's very difficult to do many scales of this computing, and the computational power is limiting our knowledge on the acceleration of particles. So hopefully in 30 years we will have solved that issue and we'll be able to see, for example, the acceleration of particles in a supernova shock or something. So that would be nice. And finally, something a little bit more exotic, dear to Angela, the energy desert. So, well, there is a whole energy desert here that lies between what we can probe with the AHC and the grand unification theories, superstring, black mass, etc. And these are being probed by, and this is where we observe ultraviolet cosmic rays and neutrinos. Well, neutrinos we haven't observed yet, but so actually, if we could, for example, observe a particle with 10 to the 22 electronvolts, this would definitely mean that there is something like new physics going on. Symmetry, extra dimensions would be probed. So this would be serendipitous discovery, but could also happen. So that's it for predictions, but yeah, I was also thinking of what we would be dreaming of. So this would be the status of the field. Then what would be our projects? I always thought about some crazy space projects. So maybe we'll be thinking of observatories beyond the Earth. I know that we already thought about them. We are already thinking about them. So, but maybe we'll be thinking about them more concretely. For example, we could launch a satellite like Gemuso, but around Jupiter. Jupiter has a larger gas envelope than the Earth, and we could gain like this, I think, 8 orders of magnitude in sensitivity, which would be cool. We could, well, so the principle of a detector like RAM is to look at Earth-skimming air showers. So it's really nice to be on the crest of a mountain. So a nice configuration would be to have a whole crater and put the radio antennas on the crest. And then I was thinking, okay, maybe we could deploy something like this on Venus, whatever. And so, and then, well, I heard this morning that, well, people talking about lunar observatories for different wavelengths, but I don't know actually if it would be possible to do gamma ray observatory there. I think it's probably difficult because the moon itself emits in gamma rays, right? The sun would kill. So, but well, why not? And also there are already some theories about using the moon as a reflector actually to make Cherenkov emission and for ultra-high cosmic rays and neutron emission in radio that we could observe on Earth. So yeah, these are grand plans that, I don't know, maybe we will be thinking. That's it. Thank you.
So our third and final panelist in the introductory remarks will be Craig Hogan. Craig was a postdoc here, roughly around the time of the 100th anniversary of the university. He's going to tell us about gravitational waves.
So I actually apologize because we were challenged to do kind of outrageous predictions, and it's way too easy to make outrageous predictions for gravitational waves. I mean, we already heard about it already today. I mean, it's sort of obvious we're going to fly at least, we're going to do incredible things. We're not going to talk about that at all. I want to be truly outrageous. I want to talk about the next quarter century quantum gravity research. We haven't talked about very much. So that was mentioned earlier. And the historical figure that we haven't mentioned yet is very important, but it's not a member of our department. It's Albert Michelson, who was the founding head of the physics department here, and also the first American to win the Nobel Prize, and of course invented the technology that we use to measure gravitational waves, interferometers. This is not Michelson, this is Henry Gale. And the reason Michelson's not, this is Michelson's experiment, but he's not in the picture because this is the end of his life. He was too frail to travel out to clearing in West Chicago. It's out near the airport. So this is an experiment that Michelson designed and Hale built winter 24-25. And it's an interferometer, and it's a big interferometer. These are vacuum tubes, the first time people use vacuum tubes to do interferometry. It's partial vacuum pumped out with water pipes. So you might ask what they were doing is, what were they doing? This is the corner station. It's kind of familiar. Its architecture is a little bit like Lego, actually. Well, it's what we would call a Sagnac interferometer. And that is a space-time diagram of it. Here's the world line of a beam splitter. This is what it looks. This is square. This is rectangular. Light comes in, and there's a beam splitter here. Half light goes around this direction. The other half goes around the other way. And then you observe the interference from that. And this is sensitive to rotation. And you can kind of see what happens. Light goes around in the space-time diagram one way and the other. If the thing is turning around, then the light going in one direction has to travel farther than the light going in the other direction. So you see if there's a net rotation, you see that and see it's an offset. So those are actually used now a lot for precision geodesy. These kinds of, but Michelson, this is Michelson's diagram from the paper, 1925. About 1,000 feet by 2,000 feet, an enormous machine. Even by modern standards, it's pretty big. But they didn't have lasers, they used arc lamps and eyeballs. It's incredible. And they detected the rotation of the Earth with this. Okay? We should have a symposium on that. It's amazing. What I want to talk about is this point, that if with modern techniques, and particularly with modern electronics and lasers and so on, superluminal sampling, you can use a similar interferometer configuration, not to study slow rotation of the Earth, but to study rotational fluctuations from quantum gravity. And the way to think about that is that they're caused by quantum gravitational fluctuations in the local inertial frame. In general relativity, there's absolute space. It's an absolute non-rotating frame in classical standard theory. And quantum gravity would produce deviations from that, and you could hope to see that in the interferometry. How would that work? Well, the way to think about that is that, like I said earlier, I don't know how quantum gravity works, but a lot of people think that it's built out of some quantum elements of the Planck scale. That's not really the same. It's not string theory. String theory actually has an absolute space background in most of the formulations. But loop quantum gravity and theories like that, there's some quantum elements of the Planck scale. And so in that case, there isn't any absolute background. So at the Planck scale, there's nothing to pin yourself down to. Space-time emerges gradually on a large scale. So in a theory like that, what you have to do, now I refer to Newton's bucket here. How many of you know about what I'm talking about, Newton's bucket? Yeah, okay. Okay, so the first mention of absolute space was in the Principia, Newton's Principia. And that was sort of in the preface to that thing he called Scully. And then he did a thought experiment. It's a really Einstein-style thought experiment, where he imagined a bucket spinning. And when you spin a bucket, the surface of the water curves up like this.
You've never seen a bucket?
And he called it a vesicle. He did it in Latin, actually. It's a Latin word. Anyway, I call it a bucket. It's a bucket. People call it a bucket. And it doesn't do that because of the bucket. It's not the force of the bucket or the force of the matter. It's because of absolute space. The water is rotating relative to absolute space. And that's still, of course, it's the same in Einstein's theory. In general relativity, there's absolute space. The difference is that in general relativity, it's all explained by general relativity in the relationship to distant matter. But in quantum gravity, it's a problem, because if you imagine going down to the Planck scale, imagine one of these buckets at the Planck scale, then matter, of course, never mind space, but matter, we know the matter is quantum. And so the bucket's indeterminate. We don't know how it's rotating. It's the certainty of the Plancking of a frequency, about a radiant Planck time. So just at that level, this is related to what we used to call quantum foam. Just the frame dragging by quantum mechanics you get rid of will make it impossible to define that standard initial frame at the Planck scale. So it doesn't exist, actually. So you know that's a fiction. It isn't this general framework. So there's something radically different that goes on from standard absolute space. And if you go to larger systems, we know it has to come out normal, but it's only approximately classical. And so we expect that there should be some non-local, exotic quantum gravitational rotational correlations that aren't in standard theory, which is a small mismatch between local and global inertial frames. And that is what you can see in the interferometer. I mean, so if you have a sagging type of cover, so you expect that to show up in a signal interferometer, not as an offset, but as a kind of noise. So another way of saying that is the signal should respond to these quantum twists in the inertial frame, and you can predict what it should look like. Even without theory of quantum gravity, because you know about the information content. You know something about quantum gravity. You know how much information about the number of states, and you know about causality. So you can predict the spectrum that we should see. Okay, so what do I mean by the spectrum? I mean, there's a quantity that you actually measure in the signal, which is the correlation function of the signal at 2 times. And so for a Sandak interferometer, the thing that you get only depends upon the path through space, because everything has to be invariant. And so this is it. I won't write down the math, but you can do the math, and this is the correlation function for a square interferometer. This is the one that we would be able to build now. Well, Steve could build it now. I can't do it. But with the parts in the holometer that we've made, you could build something that would get a correlation function like this. If there are rotational fluctuations, it's 80 meters square. It would cause an RMS, the quantum gravity calls it a 12 attometer RMS fluctuation, which corresponds to the rotation rate of about 1 radian per 10,000 years, very slow, with a peak at about 4 megahertz. So this is something we can do soon. We don't have to wait 25 years. We can reconfigure this. Right now, we're measuring with a sensitivity which has this Planckian sensitivity, which is so we can now explore exotic correlations, but it's currently we can't see rotation because it's just straight arms. You can't see the M mirrors moving that way sideways because the lamp is straight there and back. But if you bend one of the arms into another configuration like the ones I showed you, the same technology and the same parts would be able to see the effect. So something like this. So this is the calculated spectrum, and this is now switching to frequency domain. So this is 2 megahertz, it peaks at about 4 megahertz or so. And this is the amplitude of these numbers. You might think I'm just making these up, but this is the measured noise in an existing machine. Lee McCullough defended his thesis last week and convinced Cheng and his committee that this is a real measurement and this is not pretend anymore. So I think that this is actually doable, a doable quantum gravity measurement. So here's my prediction for 2042. So I'm very good prove wrong about this. But we can do an experiment to prove me wrong. So one thing is that we have by that time somebody will figure it out in quantum theory of gravity to actually do this completely from scratch, to get quantum departures of classical trajectories from classical trajectories in space-time, and we'll be studying them in the laboratory with precision. We'll have mapped it out in space and time. And it's something I've talked about in corollary. I think there's a natural consequence of this is the right story, is that the cosmological constant is just Einstein's cosmological constant. However, it's not really constant because it's quantum gravitational, and it fluctuates at about 5 kilohertz. And catch me afterwards if you want to know where that number comes from. But I didn't make it up. It comes out of known physics. And the value of the cosmological, this is the last thing, the value is not, the value is explainable. It's connected by quantum entanglement, calculable physical effects, to other constants of nature, in fact, standard model physics that we already know. And in 2042, we'll have both the other constants, the strong interaction physics, and the gravity side, and the quantum gravity side measured well enough to compare them with the degree of 3 significant figures. That's maybe a little optimistic. That's the goal. Anyway, okay. Okay, that's it.
Let's get all 3 panelists up here.
We'll have everyone.
So I think the way we're going to do this is we're going to start by asking a couple of questions ourselves of the panel. They can ask questions from among themselves, and then we'll open it up to questions from the room with whatever time we have left.
Yeah, so we have about 15 minutes, and so we'll just kind of, the idea is it's a discussion.
Right. So I'm going to start by imagining you get a phone call from some Vegas odds makers. They say, we've got some interested parties who want to put some money down on certain questions, but we have no idea what odds to give them, and we're asking your expert opinion. So you have a financial stake in this now, so to the best of your ability, tell me what the odds are that by 2042 we will have empirical insights into quantum gravity, empirical insights into the particle nature of dark matter, not gravitational interactions, and we'll have identified the origin of the cosmic ray spectrum.
So do you have a fixed total that you have to divide through?
No. You could say that you have 100% certainty we'll understand all, and 100% certainty we'll understand none. Those are both acceptable. Who's brave enough to go first?
Well, I definitely take the unit odds on all 3. It's on.
That's better.
Yeah.
That's better.
I definitely take even, these better than even odds than all those things.
How much better than even odds? I want a number.
Well, okay, so if we're haggling about this, I think I could get even odds from a lot, on a trifecta from anybody. Then you would get all 3. But at least,
I'll take what I can get.
I mean,
Anyways,
I'm not practically certain.
I'm going to take you up on that.
I'm not practically certain, but I'm not going to bet against anything.
Okay, I'm trying to remember how a trifecta works, but I think I'll take you up on that.
Okay.
Okay, so I think we'll find the particle dark matter.
With what odds? What
Yeah,
are
I
the
don't know
odds?
how, I'm not sure how I'm supposed to.
You're 90% sure, 10% sure,
90% sure.
90% sure?
Quantum gravity, I don't think so.
Let's see, 5%.
Okay, 5%.
5%.
So we have.
And cosmic rays?
Right, we got it.
She has the numbers.
What about cosmic rays?
The origin, what their sources are.
Yeah, I think that's pretty good. Yeah, I'll take 2 to 1. That we'll figure it out.
66%.
Yes. Quantum gravity, is that empirical?
Yeah, I'm not saying that there's a new string theory paper out. I mean, that's what I should help us.
That's 100%.
Well, I would say 30%. And the rest, yeah, I would say the cosmic rays, 95%. Just use it. Make it good.
That leaves dark matter.
Dark matter, yeah, pretty good as well. I would say also 80 to 90%.
Sorry, just to follow up on that.
Let's use the mic so the back.
Okay, so just following up on that, I'm just curious about the audience. So I'd like to ask the audience the same thing, but instead of having a bunch of numbers shouted out, let's just start at 50-50. So who thinks it's greater than 50% chance that we'll have empirical tests of quantum gravity? But, you know, young people, that's what you want.
There were 2. There was some
Right. So, and just to make it clear, who thinks it's greater than 10% chance? Okay. It's more optimistic than I am. Okay. So, okay, so for
greater than 1%. You should get.
Actually, I think that'd be pretty interesting.
okay, who thinks greater than 1% chance?
That's
Me
easy.
too. I guess I should ask who does not think it's greater than
But it's not a random process. How do you measure 1% probability?
So if you think it's less than 1%, if you think it's less than 1%, why would you work on it at all? Why would you do theory about it?
Yeah, Oscar.
Anybody? Never had
So let's do the same thing for origin of the cosmic rays. So who thinks it's greater than 50% chance?
What do you mean by origin?
Do you mean the high
Yeah.
rays?
The
Explain the sources.
Yes.
Yeah, so we characterize the sources. So who thinks above 90%?
Actually, I changed my mind.
Yeah, are we talking 10 to 20 or are we talking middle of the road?
I originally expressed the question as the cosmic ray spectrum, so not just the galactic stuff, but
The whole way out. All the way
more
out.
or less the whole way up.
But there's always going to be one event at the end.
That's not what I mean. I mean like,
That's the way it's worked so far, right? That's what the mystery always is. Yeah.
I thought that we needed to find the mechanism that generates those very high energy.
Yeah.
That's not so only where they come from, but what is the mechanism,
Well,
right?
if we already knew where they come from, it would be much easier to
Yeah,
understand the
but we
mechanism.
need to find the mechanism.
Yeah,
We don't
well,
know.
we're working from both sides,
The
but
computation is getting better. So we know where to point the signs.
But we want both.
yeah.
We won't go.
Okay, so dark matter, greater than 50% chance we'll see it identified.
One type of it anyway.
Sure. Right.
Yeah.
Okay, so who thinks there's a less than 10% chance that that will happen?
All right. Be on the 5 material.
It's a reasonably optimistic crowd.
You're less than 10%.
So if the LHC finds something, but we don't tie it back to the universe, that doesn't count, right?
No. it has to be
So the
done.
LHC finds something, but we can't tie it back.
That's a different, the LHC finding something
Yeah.
weird, but, or supersymmetry, but it's not the dark matter particle.
So you mean the thing that makes up all that mass in the universe?
Yeah.
To find that over.
That's right.
As part. But if it finds supersymmetry, doesn't it mean that there is a ring?
No, it doesn't mean that necessarily.
It has to be the right.
There are a couple of mysterious things that the panelists said in the talks, which I wonder if we can find an answer before 2042. So Craig talked about the connection, maybe just one sentence to clarify the perplex. Craig talked about the connection with the entanglement connection to other constants, which I didn't understand. And you talked about 10 parsecs scale features and gamma rays, which I also didn't understand. When cosmic, when gamma.
Repeat the question.
Yeah, okay, so Mario wants to know what I meant by my cryptic remark about entanglement of the cosmological constant. And so in a nutshell, it's that you can count the gravitational degrees of freedom within the Hubble radius. And if it's a cosmological constant, that's about the square, inverse square of the Hubble constant in Planck units. It's a number of degrees of freedom from gravity. And then which gives you a number which is 10 to the 122. And if you equate that with the number of degrees of freedom in field theory, the number you get is the strong interaction scale. That's the coincidence. So if the degrees of freedom are entangled and match, there's a kind of equilibration between the value of the cosmological constant from just gravity and standard law.
So you asked about the 10 parsec scale features that we see with us.
You said something in gamma, I didn't understand what you meant.
Oh yeah, I just meant that. So suppose you have something that a supernova that goes closer than 10 kiloparsec in the universe. CTA already has a resolution of 4.01 degree. If you can do a bit better, and if we are in the right range of distance, I think that we can see.
You mean you would see features of 10 parsec?
Yeah.
But supernovas are not so big. By the time they get to 10 parsecs, they are no longer.
But later.
But then you won't be able to associate with them.
Okay. No, yeah.
That's 60 years later.
Yeah.
That's for 200 anniversary.
Yeah. It's actually it's true. Well, that's true. So we have to do better in resolution.
So we have time for one more short question, please.
I absolutely don't understand what you mean and what is the mechanism of dark stars. What is what I understood they are formed by dark matter, but how that's possible that they become so big? What is the mechanism that you envision for them to become so big, and then the mechanism to emit energy or?
So
No, it's not fusion, but.
The name confuses people. They're made of almost entirely hydrogen and helium. One part intended as free dark matter. So they shine due to dark matter power, but they're actually made of ordinary. So the very first stars that form, maybe a redshift of 12, form inside these mini halos, protogalaxies. And really in the centers, in the centers you have a collapsing cloud of molecular hydrogen. And that collapsing cloud pulls in even more dark matter. And if the dark matter is made of WIMPs, then those things annihilate among themselves. And their annihilation products, a big part of that is E plus E minus and photons. So as this cloud gets dense enough, it traps the annihilation products, which then thermalize with this thing and heat it up. And it's an actual star in hydrostatic equilibrium, thermal equilibrium. Starts out maybe 1 solar mass in size, but these are weird objects. They're very puffy and cool. So they're 1080 in size, and the surface temperature is 10,000 Kelvin. So additional matter falls onto them. So they can keep growing. They have no ionizing photons coming to prevent further accretion. So more and more mass falls onto them, as long as they're powered by dark matter. So they're not hot. They're not hot enough for fusion, but they can keep accumulating more stuff. And some of them might grow to be very big, and those would be very bright. And those are the ones that could be seen in JWST. So well, not yet. That's 2018. When the James Webb goes up. I'm hoping.
Okay, so before we wrap up here, I should just point out, since Greg didn't mention gravitational waves, in 2042 that a big part of the conversation will have to do with gravitational waves. Not just ground-based detectors, maybe post-LIGO, something like the Einstein telescope, so very cold underground detectors, but in addition, space-based detectors. So I think, I would hope, my prediction is, let's do it that way, my prediction is that that will be a major part of what this sort of astrophysics will look like, that gravitational waves will have a major role to play. And I know that was discussed this morning, but just to make sure that this session at least says that.
Mention
How to check that box.
Yeah, check the box. So the box is checked. Okay, let's, before we thank our speakers, so people will be around. Katie's leaving shortly after the coffee break, so if you have burning questions for her, you should chase her down. But otherwise, we'll keep the discussion going, and let's all